Most of the time when you make projections or predictions, you want to penalize the values that are further away from the actual value more and more than those that are closer to the actual value. To do this, there is a handy equation called the root mean squared error, which takes the mean of the squared error values. In this equation, you first take the difference between each projected stat and the actual stat, aka the error. We square this difference, aka the squaring part. We take the mean of all the squared differences, aka the mean part, and then we take the square root of that mean, aka, you guessed it, the root. Let's look at an example to calculate the root mean squared error for our points projections. We will first read in the data frame that has our projected points and real points for each player in the 2018-19 season. If you recall, I ran this offline since it was going to take a little while. So we can import our modules, and then we want to read in the CSV, which is the player projected DF CSV. And as you see, it has the projected stats and then the real stats for our players. So to manually create the root mean squared error step by step, we first need to take the difference between the projected stat and the actual stat. That means to get the projected points, we could take the projected DF, where we take the projected points, and subtract the real points, which is the points column. So that's how we will get the difference, which will be the error value. And let's save this as a new column and call it the squared error. And to actually square it, we need to run that. So now the next step is getting the mean, which means now we have this projected DF squared error column that we can call the mean on. And let's just save this to the mean squared error, and we'll run that. And I have a typo, and we run that. And then what we want to do is get the square root of that mean squared error, and we will save this as the root mean squared error. And again, if we print this, we see that our root mean squared error for our points projections was 3.3. So let's compare this to our assists column. So let's run the same thing for our assists. So if we take our projected DF and we get our projected assists, and then we want to subtract the actual assists, and again, we're going to square that. And we can just overwrite the squared error that we had created before. And then to get the mean squared error, we take this squared error column and we get the mean. And then again, the root mean squared error is the mean squared error, getting the root, the squared root of that. And if we print this, we see that our root mean squared error was a little lower for the assists, meaning we were closer to the assists than points, which makes sense since the points are going to be more widespread, which it's a little bit difficult than that bigger number. Now, instead of calculating our model effectiveness manually, we can use a handy function from the scikit-learn module. Scikit-learn is a great module for anything data science and machine learning related. And really what we're going to do is take a specific mean squared error function from the scikit-learn library. So this time we are going to import from sklearn and the specific metrics import, and this is called the mean squared error. And then we're also going to want to import the square root function from math. So let's run this. And our mean squared error function is going to take two inputs, a list-like object representing the true values and a second list-like object representing the predicted values from our model. This function will make things quicker and simpler since it's built exactly for this cause. So again, let's read in our two data frames which have our projections in one and our player info in the other. Again, this was coming from the previous lesson, but you can find these CSV files in the resources. Then what we're going to do now is split our projection data frame into two separate data frames. One with the real projections, aka the true values, and the other with our projection stats, aka our predicted test values. This will allow us to use each as an input into our mean squared error function. So to get our real values, we can take our player projected data frame, use our handy loc method, where we're going to want all the rows. However, we are only going to want a certain subset of the columns, which again, you can see we have our real columns don't have the PROJ in front of it, whereas our projected columns do. So if we pass in all of our real columns, we can now save this as df real. And that means similarly, to get all of our projected columns, we want all the rows, and we would do the same thing, only this time passing in all of the projected column names. So it's the exact same columns, they just have the PROJ underscore before it. And this one, let's save as PROJ, and let's run both of these. Great, so now if we kind of looked at a sample of df real, and we looked at a sample of df projected, you'll see we have the same columns, which allows us to pass these into the mean squared error functions. We can pass in these data frames with the test and predicted, and then what we want to do is get the mean of this value and then the square root of that value. We'll save this as a variable confidence and add a nice string to help us understand our confidence. So we get our squared error. We can call the mean squared error function directly since we imported it directly, and we're going to pass in the real data frame and the projected data frame. And then to get the mean squared error, we can call numpy mean on the squared error. And then to get the root mean squared error, we can call the np square root on the mean squared error. And again, let's just save this confidence equals the root mean squared error. And what we're going to want to do is we can print with the confidence. And so for our projections, as they are, we have a 98.03% confidence in our projected per game stats. So let's just group this together so we can run it again in the future. Since we were just seeing the pure values in our projections, it would be nice to get a gut check of how we're doing to make sure it passes the eye test. Let's concatenate the real and projected data frames with our player info data frame so we can see the names and numbers. So to do this, we'll call the pd concat, and it's going to take our player info data frame that we previously read in, and then let's also read in our df real, and again this axis is going to equal 1 to show it's the column, and let's save this as the df real stats. And the one thing, if we were to look at this df real stats sample, our projected season ID, let's rename that to be just season ID. So if we did the df real stats rename columns equal projected season ID, and we want to change that just to season ID, and we'll call this in place, we're okay just updating it. And for our projected data frame, let's also rename the columns to make it easier on the eyes. So to get our df projected stats, we'll concat, again, the player info with our df projected data frame. And this is with axis 1. And basically what we're going to want to do is rename all of the projected columns and just drop that projected to make it easier. Now we can print the top 5 rows and match it up to see how we did. The real stats are on top and the projected stats are below. So if we display df real stats, we'll take those first 5 rows. We see we got Aaron Gordon, Al Horford, Al Farouk Amino, Alex Burks, and Alex Abrines. And let's display our rounded df projected stats to 1 space. We'll just get those first 5 rows. And these are our projections. So looking at just the points column, Aaron Gordon, his real stats were 16. We projected 16.1. Horford's were 13.6. We projected 12.3. Al Farouk was 9.4. We had 9.8. Burks 8.8. 8.3, and Alex 5.3 and 5.5. Awesome. Let's now compare it to a competitor to see how we're doing at more of a macro level.